All right, welcome back, everyone. Today we're going to be talking about Riemann sums. Kind of continuing our talk about antiderivatives and kind of the applications of what they can be used for. If we look at this right here, okay, we found out the other day that that basically gives you the antiderivative of a function. Sometimes that can be referred to as the indefinite integral. Now here, what they did is added in some limits talking about the integral from a to b. That is actually going to give you the area underneath the curve bounded by the x-axis from the point A to the point B. So if we looked at it, say I had a graph, and I'm going from A to B, and say here's my graph, that integral is going to tell you exactly what that area is. So one thing that we can use to kind of estimate that area is Riemann sums, and that's what we're going to be talking about today. So there's 4 different types of Riemann sums that we can look at: left hand, right hand, midpoint, and trapezoidal. So basically the idea is if you use a rectangle, or in the last case, a trapezoid, to basically split up what it looks like. You split up your area underneath the curve using rectangles, and you can find the area of each individual rectangle that you're using, and then just find the area and add them all up. So the first one that we're going to look at, left-hand Riemann sum with intervals of length of 2 units. So the graph of f of x is pictured there below. And we are going to estimate the area on the interval from 1 to 7. So from 1 to 7, if I were to extend that up, we're basically going to be looking at estimating this area bounded by the x-axis and our curve. That's the area that we're going to estimate. Now here in the next lesson, what we're going to do is actually going to figure out how to get the exact answer. But for right now, we're just using just estimates of it. So to start, left-hand Riemann sum of subintervals of 2 units. So if I go from 1 to 7, the rectangles that I'm going to be drawing are going to be 2 units wide. And the fact that it's a left-hand Riemann sum, what we have to do is we're drawing the rectangles with the top left-hand point of your rectangle touching the curve every single time, and the width of it has to be 2. So if I were to draw this, my first one, starting at 1, see right there, the top left-hand corner of my rectangle touches the curve. Then I'm going to draw the next one. There's the next rectangle, top left-hand corner of the rectangle is on the curve, and then the last one is right there. So we can see that's not going to be an exact area of that area that's underneath the curve, because we have a little bit right here would be short. Right here I have a little bit too much area, and then over here I have a little bit too much area as well. Granted, this is over, and this one's under, so it would be pretty close to the actual area, but that's what we're doing. So we're estimating. So we have the integral from 1 to 7 of our function is approximately, and now I'm just going to basically find the area of each rectangle and then add them up. So the very first rectangle we know is 2 units wide times the height of that rectangle would be given by that function value right there, which is f of 1. So 2 times f of 1, that would tell me the area of this first rectangle. Then I'd have to add that to the next rectangle is 2 units wide times the height of it is given by that function value right there, which is f of 3. So now that would tell me this area. And then the last rectangle is 2 times the height of that rectangle is given by right there, which is f of 5. And if I added those up, I'm going to get the actual area. So the nice thing is, when we're talking about a length of 2 units, we know that the width of every single one of those rectangles is the same. So we can actually even write it as 2, because I can factor out a 2 out of every single one of those. 2 times f of 1 plus f of 2. Sorry, f of 3, not f of 2. And then plus f of 5. And you can do that just because it's going to make your calculation a little bit easier to get your answer. So when you actually add all of that up, we get 42.667. Which I know the first time I saw that, it seemed like it was a lot, but when you actually go in here and look, I mean, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It starts to add up pretty quickly. So that's a pretty good approximation of the area. So that one was just a left-hand Riemann sum of 2 units wide. So we would do the same thing here. And I'm just going to talk about this real quick, and I'm trying to cut the notes down a little bit shorter than what it was the other day. When I was done the other day, it took me 40 minutes long to get through the notes. So I'm trying to be a little kind to you guys and try to get through it a little bit quicker. So if I were to just draw, if we were to do the left-hand Riemann sum with intervals of length 1, we just have to remember, since it's a left-hand Riemann sum, that the rectangles that I'm drawing, the top left-hand corner of my rectangle is going to be on the curve every single time. So I'm just going through here, just drawing my rectangles from 1 to 7. The top left corner of every rectangle is on the curve. So if we were to actually find this one, we know that the integral from 1 to 7 of f of x dx, and that's just talking about the area underneath the curve from 1 to 7, is approximately the width of every single one of those rectangles is 1. So I can go ahead and factor a 1 out of every single area of the rectangle. So I have 1 times, and then the inside here is just going to be all of your function values of where you're actually finding the height. So for this one right here, I find the height by using f of 1, and then I would have plus f of 2, plus f of 3, plus f of 4, run out of room here, plus f of 5, and then plus f of 6. And then that would be my last one, because this area of this rectangle right here, the height of it was found by using f of 6. I'm not using f of 7 at all with this one, because that's not a function value that we really need to worry about. So I get the area of this one is approximately 41.667, which is probably a little bit closer to the actual area, because if you look at the rectangles that we're drawing, the space underneath, let's change colors here. The area underneath, a little short, little tiny bit over, a little bit tiny over, a little bit over, a little bit more over. We're getting closer to the actual function value. So this next one here, left-hand Riemann sum with subintervals of half a unit. This one's going to be pretty tough to draw, but here we go. So every rectangle that I'm going to draw is a half of unit wide, and the left-hand point of my rectangle, top left-hand part of my rectangle, is on the curve every single time. So you can probably guess, as we make our intervals smaller, we are slowly getting closer to the actual value of the area underneath the curve, just because the points that are over and under are just getting closer and closer and closer and closer to the actual real value. But you can see here, this one's going to be quite a bit of work. Almost done. And there it is. So getting pretty close to the actual value. So if I were actually estimate the area, and I'm not going to write this entire thing out, but you guys will get the idea. You know, the area underneath the curve from 1 to 7 is approximately, we have 1/2 is the width of every single one of those rectangles. Then I would have f of 1, because that's my first rectangle, plus f of 1.5. Then I would have to go all the way up to f of the last height of the rectangle that is given from the left-hand side would be 6.5. So that area is 40.917. I'm getting closer to the actual value. All right, so that's the left-hand Riemann sum. The next thing is just going to be the same thing, but the right-hand Riemann sum. So let's talk about the one that has 1 unit as the width. So when I change it to right-hand Riemann sum, I'm basically drawing the area, and I'm using rectangles that are one unit wide. But now the corner that I'm going to draw my rectangle from is the top right-hand side. So the top right-hand side is going to be on our curve every single time. So just kind of changing the way that we draw it a little bit. And we're going from 1 to 7 still. So there would be all of my rectangles that I need to find the areas of. Notice that my rectangles are drawn by the top right corner of every single rectangle is on the actual curve. So we would have the area from 1 to 7 of our curve is going to be approximately, the width of every single one is 1. And now I just need to add up my function values of the heights of each rectangle. So I would have the very first one would be this one right here, which is f of 2. And then I would go all the way up to the last one, which is found by f of 7. So the area in this case is 37.667. So with intervals of 2, it'd be exactly the same. We'd just start, every single rectangle that we need to draw would be from the top right-hand corner. This is what it would look like. And there's what it would be. Then I'll find the area of each one of those rectangles and add them up. If we look at this one, just happens to be the right-hand Riemann sum. It's probably going to be under what the actual value is, because this area right in here is way larger than that area that's over. So the half would be probably getting closer to the actual value here on the next page. Let's get that. There we go. Be getting closer to the actual value the smaller that the widths become. So before we continue, what inference can you make about the approximations of the lengths of the rectangles decreases? So like exactly what I just said. as the width of the rectangles decrease, you're getting closer to the actual area of underneath the curve. All right, and then graphically, why do you suppose that is? It's because the smaller the length of the rectangle, the less, I guess, overage and underage area you seem to have outside of the region bounded by the curve and the x-axis. So moving down here to midpoint. Midpoint is really, it's the same concept, but the way that we draw our rectangles now are going to be based off of the midpoint, the middle of the rectangle. So before, the left-hand Riemann sum was based on the fact that your top left-hand corner was on your curve every single time. The right-hand Riemann sum, the top right-hand corner of your rectangle was on your curve every single time. When we get to the midpoint Riemann sum, the middle of the rectangle on the top needs to be on your curve every single time. So if I look at, we'll do this length of 1. We'll do this one. And I'll probably skip the other two, just kind of save time and just make the notes a little bit shorter again. So now I'm just doing the same thing, but the middle of our rectangles from 1 to 7 need to be on the curve. So in between 1 and 2, right there is the middle of our rectangle. In between 2 and 3, there is the middle of our rectangle. So that's how I'm drawing my curve, is based on the middle of the length of 1, halfway in between that. 1.5, 2.5, 3.5, 4.5, 5.5, which I just did. And then the last one would be 6.5. So when we go to actually do our work to figure out the area, we have the integral from 1 to 7 of f of x dx, and all that represents, remember, is just the area underneath the curve from 1 to 7. But now the width of the rectangle is still 1 every single time, but the height of each rectangle is given by the midpoint. So I would have f of 1.5, because that's the height of where I found the height of my first rectangle, plus f of 2.5, all the way up to f of 6.5 is the last one. So the area of this one is 40.167. So right now you probably would have a good idea in terms of which Riemann sum would give you the closest to the actual value. I mean, obviously, I think the midpoint one, just because the overage and under kind of gets offset with every single one. And that's probably going to be pretty close to our actual value, which is that 40.167. Then the last Riemann sum that we're going to talk about is a trapezoidal Riemann sum. So we'll look at one of those. We'll do the 2 units wide one. Remember, the definition of a trapezoid is really just one set of parallel lines, and that is it. All right, so this one right here, we are drawing our trapezoids with a height of 2 units. So from 1 to 3, that would be the height of your trapezoid. So I'm just going all the way up to our function value right there, all the way up to our function value right there. There's the bottom of our rectangle. And I just connect and make a straight line. So I do the same thing with the next one. I'm going from 3 to 5. So I go up to where 5 is on our graph, and then connect it to f of 3. And then the last one, f of 7. And I connect it. So we can see there, we got 3 trapezoids. So if I go to actually find the area of each trapezoid, we just have to remember the area of a trapezoid formula, which is 1/2 times the height plus, or times, you add the bases together. 1/2 the height times base 1 plus base 2. That's the area of a trapezoid. So those are my 3 areas that I need to figure out and add. And we could really see, well, I'll go ahead and do this, the entire thing, and then I'll kind of factor out what's in common. So the very first one, I would have 1/2. The height of that trapezoid is 2 units, because that tells us right here. So length, yes, but we're really talking about the height of the trapezoid. Times, we have this length right here from here, which is f of 1, plus f of 3. So there's my area of my first trapezoid, and I just do that again. Plus 1/2 times the height, which is 2. And then my 2 function values here for this next one are f of 3 plus f of 5. That's my 2 bases of those trapezoids. And then for the last trapezoid, we would have 1/2 times 2 times the 2 bases would be f of 5 plus f of 7. So we do have something that's in common with all of those. All of those have a 1/2 and a 2, because that's the height of every single one of them. So if I factor all of those out, what I have left is I really have f of 1, and that's the only time that I use that as a base. Then I have f of 3, but I'm using that twice because it shows up as the base of 2 different trapezoids. Same is true with f of 5. It shows up as the base of 2 different trapezoids. And then we have f of 7 only shows up as the base of a trapezoid once. So our area in this case is approximately 38.667. All right, so there are the 3 different approximations of the area that we can use using Riemann sums. Left-hand Riemann sum, right-hand Riemann sum, midpoint Riemann sum, and trapezoidal Riemann sum. Each kind of are a little bit unique. So what we're going to do here is we're going to move down to a couple of examples. So this is kind of just talking about on this slide, hey, what were your actual areas every single time? Do you think it was an over or under? And then which one do you think is the exact one? Over here on the right-hand side in that box, they're just kind of talking about, hey, we're going to come back to this after this next lesson, after the next unit, and actually find out the exact area of the region that's bounded by 1 and 7 and the curve and the x-axis. But we're going to do that after the next lesson. So moving down here to an example. And this is it. We're almost done here. There we go. Here's our example. So the first one, given the table of values below, approximate each definite integral by finding the indicated Riemann sum. So the first one says approximate the integral from 0 to 25 of f of x dx using a midpoint sum in 3 sub-intervals. So the first thing that we are going to do, and it doesn't necessarily have to be equal sub-intervals, but here we have, 1, 2, 3, 4, 5, 6, 7. I got 7 different function values that they give us. So I want to break it up into 3 intervals. So I can go from 0 to 7. I can go to 7 to 15. and I can go from 15 to 25. Now, the width of each one of those rectangles are different from each one of them, but with this one, I want my actual height of the rectangles to be given by the midpoint. So I'm just going to use literally the middle point to find the height of the rectangles. So here we go. The integral from 0 to 25. So the area under the curve from 0 to 25 of f of x is approximately the very first rectangle that we have. I'm going from here to here, so that's 7 units wide. And the height of my rectangle is given by the midpoint. So I want this value, 6. Plus the width of my next rectangle is going from 7 to 15, which is 8 units wide. And the middle of our rectangle is right here. That's my function value. It just happens to be negative 10. Plus the width of my last intervals from 15 to 25. That is 10 units wide. And the middle of our rectangle, the function value is going to be 8. So when I add all of those up, it is approximately 42 units. So probably the one thing that sticks out initially with this problem is that middle one. This area right here is a negative, being negative 80. It hasn't really come up yet, but it is right now. Anytime you're finding the area underneath the curve, if the region that is bounded by the x-axis is above the x-axis, we normally have a positive area. And if the area that's bounded by the curve in the x-axis is below the x-axis, that's when we end up having a negative value. So that probably just means, we can see here in between 4 and 7, right in here, in between 4 and 7, we go from a positive to a negative. So that graph definitely crossed the x-axis, and we're working with all negative values. So we would expect our area for this middle rectangle that we drew to be negative because it is underneath the x-axis. All right, so let's look at B. Approximate the area from 0 to 15 using a left-hand Riemann sum and 4 subintervals. So I want to break this up into 4 different areas. And the first thing is, it says we're going from 0 to 15. So these last 2 columns mean literally nothing because that's not talking about in between 0 and 15. So now I want to break it up from 0 to 15 into 4 groups. So I can go from 0 to 4. I can go to 4 to 7. I can go from 7 to 12. And I can go from 12 to 15. That would break it up into 4 groups. And like I said, it doesn't have to be 4 equal subintervals. It's just talking about 4 subintervals. So I have the area under the curve from 0 to 15 is approximately the width of the first rectangle would be 4 because 0 to 4 is 4. And I need to find the height of the rectangle by the left-hand corner. So this would be 15 in this case. And I have plus. I'm going from 4 to 7 for my next interval. So that is 3 units wide. And the left-hand top corner would be at 6. Plus going from 7 to 12 would be 5 units wide. The left-hand corner would be negative 5 in this case. So plus the last one from 12 to 15 is 3 units wide. And the left-hand corner would be all the way down here at negative 10. So if we add all of those up, all 4 of those areas, we are at approximately 23 units. All right, 2 more examples and we'll be done. Get rid of this up here. So this next one here, going from 4 to 20. So it's kind of like the previous problem. This column right here does not matter, and this column right here does not matter. And we are talking about 4 subintervals. So I want to break it up. I can go from 4 to 7. I can go from 7 to 12. I can go to 12 to 15. And I can go from 15 to 20. There's 4 rectangles that we could be drawing, and there's the widths of each one of them. So I'd have the area from 4 to 20 of f of x dx is approximately, let's see here. The width of the first rectangle from 4 to 7 is 3 units wide. And now we're talking about a right-hand sum. I have to find the height of the rectangle from the right-hand side, which would be -5. Plus my next rectangle is going from 7 to 12. That is 5 units wide. And I would find the height of it from the right-hand side, which is -10. Plus the next width of the rectangle is 12 to 15, which is 3. And the right-hand side of that rectangle would be all the way at -2. And then plus the last interval is 5 units wide. And I would find it from the right-hand side, the height, which is 8. So we are approximately at -31, which all that tells you is the majority of the graph in this case is below the x-axis. All right, so the last one here, let's scroll down, is using a trapezoidal sum. Cooper, no. It's my dog barking. Our neighbor just pulled in the driveway. Okay, so the last one, trapezoidal sum of 3 subintervals going from 0 to 25. So I need to figure out, all right, what's a good way that I can break this up from 0 to 25 using kind of 3 intervals. I can go from 0 to 7. I can go from 7 to 15. And I can go from 15 to 25. That's probably the easiest way to break that up into 3 intervals. And I want to make sure I overlap and I'm not missing some areas there. All right. So I have the area from 0 to 25 of our function. So the area that's underneath the curve from 0 to 25 would be, with this one, the heights of each one of them are a little bit different, so I can't necessarily write it as 1/2 times the common height. So I'm really going to have to find the area of each rectangle kind of individually. So I would have 1/2. The height of the first trapezoid is from 0 to 7, so that's 7 units. And then times the base from 0 to 7. 15 is the first base because that's at 0. And then plus -5. That's my base of the other end of the trapezoid. Plus 1/2. The height of the next trapezoid from 7 to 15 would be 8. And then the base lengths would be the function values at 7 and 15. So I have -5 plus -2. And then plus the last one, 1/2. The height of the last trapezoid is from 15 to 25, so that difference is 10. And the 2 bases would be the function values at 15 and 25, so -2 and 20. So this is approximately 97 units. All right, so that's the end of the notes for today. Like I said before, if you have any questions, just rewind and watch it again. If you do have questions, make sure you are emailing me. It's your guys' responsibility now to really look at and complete this day 48 homework. So you guys need to do this day 48 homework, copy down the notes, do the homework, and let's say that this homework needs to be turned in to me by Monday at midnight. Just to clarify, that would be, midnight in between Monday and Tuesday. So on Tuesday of next week, we are going to be looking at this section right here, applying the fundamental theorem of calculus. And basically what this section is talking about is finding the exact area underneath the curve. So that's it. Just copy down the notes, start working on the homework, and please get that to me as well. So far, I need some more homework turned in from you guys from the last section as well. Just make sure that you guys are trying to stay on top of your work as best you can, because remember, we're going to be continue to get stuff because we haven't heard anything in terms of the AP tests. The date's probably going to be extended, but it almost sounds like they're going to figure out a way for you guys to be able to take this test at home, which would be extremely nice for you guys, because obviously if you're sitting there at home, you would have all of your notes, and you could, I don't even know exactly what that's going to look like yet. So that's kind of what we're just hearing right now. So if you have any questions, though, just get a hold of me. Hope you guys have a good weekend.